Hi, I'm Rich with insideHPC. We're here at ISC 2017 in Frankfurt, and I'm here with Dr. Eng Lim Goh. Eng Lim, welcome to Germany.
Yes, thank you. Good to see you again. Yeah. Well, this must be what the fourth or fifth in the sequence, huh?
Yeah, it's like every 6 months we kind of check in and see what your thoughts are on these growing trends of HPC and big data and convergence with AI and machine learning, all this stuff. Yeah. But today I wanted to ask you about some recent announcements with HPE, your new employer, right? That acquired SGI. This PathForward award that you guys won. Can you tell me about your role there and what is it all about?
Well, it's a huge award, right?
Yeah.
The PathForward is an exascale computing project program that funds research and accelerate it so that we can get to a capable exascale machine in the right time frame and right power envelope. Yeah, and it's a $250 million of the order program, of which HPE is one of the 6 recipients. So this is a great win. Now, in terms of what we do there, we can't talk directly about it, but you can get some ideas from the HPE labs work. There's some of which has been moved to the products group under Bill Manel now. In there, public information includes focus on bandwidth, right? I think that's the key, bandwidth, both vertically within a node and bandwidth horizontally across nodes. Let me elaborate on vertically within the node. Now, as you get to exascale, bandwidth is going to be the key in order to get capable systems performance. Yeah. And one way to get bandwidth is to look at within the node the memory hierarchy that's coming up. Now we have our normal memory, volatile memory in the form of DIMMs, but the non-volatile one that are slightly slower in the form of DIMMs but much bigger are coming out, right? Intel has their 3D crosspoint. There are some working on phase change alternatives and some working on resistive RAM alternatives, right? So that one is another level in hierarchy. And then above the typical memory DIMMs, there is also high bandwidth memory that are stacked. Now, this one is going to be one of the key ways to get application performance, because the memory bandwidth you're getting from the DIMMs is starting not to keep up with the increasing hunger of the CPU. Yeah. And high bandwidth memory that are stacked much closer to the CPU is going to be the answer. So lots of investigation required within the node to figure out which level in the hierarchy to invest in and which level in hierarchy perhaps to remove, so that you don't have too many levels, in order to maintain bandwidth and have good latencies. So that's within the node. Then there is the horizontally across nodes. Yeah? What do we do? Again, you have focus on bandwidth, maintaining bandwidth as you improve towards exascale compute capability. As you improve bandwidth vertically, we also have to improve bandwidth as you go across nodes. Now, this one is also another challenge, right? One way to keep up with bandwidth when you have multiple CPUs talking to each other or multiple compute units talking to each other is bring it closer. So logically, one way is to bring the GPU into the CPU package or socket. That's the first thing you do. Yeah, logically, right? The next logical thing would be to take the fabric interface chip or the network interface chip that's currently outside and bring it into the socket or the package. So you keep bringing things in. And you're already starting to see Intel doing that with OmniPath. How about the other vendors, right, that have no access to OmniPath? That's part of the reason why we came up with Gen Z. Yeah, as an open interconnect, others can then adopt to bring into their own socket and their own package. So you bring the GPU in, logically that you should do that to get bandwidth. Then you bring the fabric interface chip in. The next thing now, once everything is in the socket, how do you then connect to other sockets of the same kind or different kinds? And this is where the topology comes in. Now, research in topology is absolutely important now. Now we've done very well at SGI with Hypercube. Yeah. Although I don't know if you remember, we've been criticized for using the Hypercubes, and until Jack Dongara suggested a new benchmark from HPL that ranks the top 500 to HPCG that to rank the top 500 that stresses data and balance of the system a bit more.
More representative of a real machine workload than Linpack, which doesn't really care about I/O, for example.
Yeah, that's what Jack Dongara focused on, right? The more balanced system measurement, HPCG. And I couldn't sleep for 3 nights, right? Because of I've been defending the criticism against Hypercube. And if HPCG came out and we were re-ranked on HPCG and we dropped, right, in the rankings with the HPCG benchmark relative to HPL, then my critics would have been proven right. So the 3 nights that we were waiting for the result, I couldn't sleep, right? Now, I just said, all we needed to do was to stay at the same level.
Yes.
Don't move, don't drop, right?
Okay.
It turns out our top 3 systems all climb multiple places in the ranking. So this tells us we are currently on the right path with Hypercube. It is a lightweight interconnect, right? But a heavyweight, when it comes to application performance. Lightweight because of cost, Now in Exascale, right, there is one issue with Hypercube. And that is, by the time you grow a system from 10,000 nodes, 100,000 nodes, right, or more, right, the number of hops in the dimension of the cube, because of the increasing dimension of the Hypercube, means that you may end up with 11 hops, 12 hops, 15 hops to the most remote nodes in the system.
Sounds like a lot of latency potentially.
Yes. And this is where then we have to figure out a way to solve it. And this is where HyperX is a published topology of HPE Labs, which the way I see it is a variant of multidimensional all-to-all. And another way to look at topologies are all related. And also, in a way, it's a variant of Hypercube by growing the interconnects out here. And so you can see a progression, possibly, since it's published. We ship Hypercube today, progressing towards a multi-dimensional all-to-all, which is what HyperX is. Now, given that, there is a problem, right? Every topology you pick, you have to try and fix or adapt to the problems that it has. The problem it has is the issue of huge number of connections. Hypercube has it. Multidimensional all-to-all will make it even worse. We're talking an exascale system of the order of, naively, right, order million cables, right? A million, right? We did nothing about it, right? Okay. What makes it worse if you don't have an affordable optical interconnect solution? You can't do it with copper because a million copper cables is costly. Moreover, you'll be limited in length. So the thing we have to do is to use. It's published. We are in HPE Labs working on coarse wave division multiplex towards dense wave division multiplex, which allows you to use one cable to send to represent many cables that are going across the different racks in the system. So if we can do a 10-to-1 reduction, a million cables becomes 100,000 cables, right? It starts to get more manageable. Today's system are of the order of tens of thousands of cables, the bigger systems. So getting to 100K, bringing a million down to order 100K, starting to look feasible. And that's the first area of research that's well known within HPE Labs. And the other area of research in optical silicon photonics in particular is to bring that cost down and power down. Because if we don't, if we use today's straight-off VCSEL technology, we're talking, megawatts.
Just for interconnect.
Just for the interconnect, right? And hundreds of millions of dollars just for the interconnect, right?
Not practical.
So in addition to coarse and dense wave division multiplex, to reduce the number of cables we use so it's more manageable, we have to reduce costs and reduce power. So 3 things. Quantity of cables, power, used by the interconnect, and cost. And this is the research. The research isn't so much to invent a new optical approach. This is well known now. The focus is to engineer to reduce these 3 things. Yeah.
come to that
And all
optimal.
this come together. What goes towards our HPE labs, HP labs research going towards exascales. Yeah.
Wow. So I'm just thinking about how much would a million cables, copper cables, weigh? You're talking metric tons of.
There is weight, there is power. The electricals to drive those cables, or the electricals to convert to optical to drive those cables. The cost of the cables. Well, length of cables, copper is measured by the length, right? And then optical, the cost is at the ends of it. So the goal for optical cable that we are working on is to reduce the cost at the ends, because in between is essentially glass, well-engineered glass, but copper costs money. The longer the cable, right, the more it costs. Yeah.
And reliability as well, right? I mean, just you'll be fixing cables for months,
If you
right?
look at MTBFs, right? If you go from a 10,000 cable system to 100,000, a million, you are talking an increase of multiple orders in quantity, and therefore correspondingly, if your MTBF doesn't improve, multiple orders reduction in reliability, right? Yeah. So we have to reduce the quantity, let alone the cost and the power. Yeah. So that has been the work going on. Yeah.
Yeah, it's exciting that you're getting this PathForward money to help you develop that, and you've got to kick in 40 cents on the dollar yourself, right? It's not.
That's a co-design, co-development effort, and it has all to do with intellectual property also. When we contribute that much, that way we have more access to the work for the work we put in. Yeah.
Well, great, Eng Lim. The second thing I wanted to ask you about was the machine, because the press releases kind of tied that as to why they were interested in HPE, right? And the machine has come out as a prototype since we last talked. And can you bring us up to speed there?
Yes. It was published, right? Announced, and Meg Whitman made a description in announcement, and Kirk Bresnicker, the chief architect, was also in the announcement. But what I can add to that is the following, right? You see, if you in the traditional high performance computing world, all right, something that I've described in our previous interview. You have this cone of data, right? Small amount of data goes in, and then you apply supercomputing power in your formulas and partial differential equation to do your calculation to produce a prediction on the right that has massive amounts of data, right? Then after you've done that cone increase, right, you have to take that massive amount of data and then run analytics to reduce that massive amount of data back out to an insight. The insight could be just as few little data as 3 bits, right, or 2 bit or 1 bit. This thing is good or no good, right? Yeah. Right. I'm just exaggerated. Or you essentially on this end of the cone, you push in a haystack and you try to get the needle out at the other end. So you got these two sides, right? Yeah. So HPC simulation running supercomputing power onto partial differential equations to generate massive data. And then from the massive data, you run analytics or machine learning or artificial intelligence to get at your insight at the end. Now, if you notice this expanding cone and then a reduction, right in the middle is that exabyte of data in an exascale system. You won't want to. You won't want to move that data.
Moving that over wire would no.
Yeah, it would be impractical. Now, if you look at that center part where this massive amounts of data, now you realize why the machine was very insightful the foresight of HPE to think of the machine at that time. Because right in the middle, if you imagine all that in memory, if you can afford the memory, of course. Right. In memory, there you have the machine. Essentially, you put all that data in that same single architecture, to which then you put processing elements around it. Yeah. Now the key, of course, is to how to get towards petabyte, hundreds of petabytes of memory, and make it affordable. And that's the other research that we mentioned earlier. Non-volatile memory, they are much higher in capacity than normal typical memory that we know of, albeit slightly slower, right? Imagine all that in the middle, the cone going up and then all that in the middle in one single memory, to which you bring your HPC operators and your analytics operators to it. That essentially is the machine. Yeah. So that's the motivation really. Recognizing the fact that even in an exascale system, data is going to be the big ticket item to solve here. One of the big ticket items to solve. And the machine architecture, the prototype architecture, is a concept that helps us to get there, to help alleviate this issue. Yeah. Yeah.
It's pretty exciting to see these things coming together. And I went to HP Cast and they were talking about how they integrated the SGI product line into what they're doing. And at the very top is the what we used to call the ICE XA, right?
The product is there,
Yeah.
and it's now called HPE
Yes.
SGI 8600. Yeah. So for those customers who see that name, be reassured that it is the same ICE that they are used to. Yeah. And to sum it all up, so we've got individual labs, research work, all right, that has a lot of foresight in it, invested a long time ago, and now coming to fruition towards an exascale, contribute towards an exascale system, a capable one. There is the machine architecture that takes a step back and looks at the data flow, which is the result of workflow, and you're starting to hear more and more of that from the DOE, focusing on workflow but not just the application workflow. And for us, when we look at workflow, we look at data flow, how the data flow, the machine, right? And then finally, I must emphasize this one. We talked about it at SE16 interview, and that has to do with energy efficiency.
Oh, yes.
Yeah. Now, why is this important? Well, you know, we work so hard, invest so much money by the different processor vendors and interconnect vendors to try and eke out and reduce picojoules per flop or picojoules per bit. We work so hard, hundreds of people, thousands of people working so hard to just try and extract and reduce picojoules, right? And of course, when you have large quantities of it, you start to save a lot. But now, don't forget, if your entire system's architecture put together is 3% less efficient, yes, a 30 megawatt system, right? Just 3% less efficient in running the system electrically, you are wasting a megawatt. Yeah? So people don't internalize that, right? Here you are working so hard at the picojoules level, and then if you just relax in the system design, you just throw a million watts out the window, right? And we have been focusing with the ICE XA energy efficiency all these years. Now we are now waiting anxiously for the top 500, green 500 number to come up and see who is number one there, right? Or at least where we stand up there. Do tell your readers to watch that list, yeah, because 3% of 30 megawatt exascale system is a megawatt.
Wow, and that's real money. Yeah, yeah, very interesting. Well, great. Well, that's pretty exciting, Eng Lim. I'm really glad we could get together and do this again. And it's like in the enthusiasm in your voice. It's almost sounds like you've started a new job, and I'm really happy for you.
HPE has been great.
Yeah.
So, a company that we have very senior engineers, right? Their talent all recognized at HPE, even the junior engineers, right? And have been treated appropriately. And I think this is something to must say for HPE here.